So a transformation of functions happens when you put a multiplication factor either in front of the function or inside of the operator in order to modify the effectiveness of the x value within the function, or to modify the effectiveness of the function's output when you graph it. So what that looks like is expansions and compressions either horizontally or vertically of the basic pattern. So where translations were simply moving the thing around, a transformation actually dilates or compresses the function and changes its shape. That's what this sort of Latin means. Trans is to move across, and formations is shapes. So you're moving across the shapes. So it will actually be a change in shape. All right, so the first translation or transformation we're going to do is a vertical stretch, and I'm going to use a logarithm to show you that one. So I need my basic pattern for log. So you're going to have to think about those x values that work really well for log. So the first one is at 0, there is a vertical asymptote. And then the x values that are really nice will be 0.1, 1, and then 10. So the log of 0.1 is -1, and the log of 1 is 0, and the log of 10 is 1. You can check those with your calculator. So what I've got in these charts here then are some x values, and then I have the log of those x values. And the function that we're going to try and sketch is g of x is 3 log x. Now you notice it isn't log x plus 3, it's 3 times log x. So when you see a number multiplying in front, it is affecting the function vertically, because you are taking the output of the function and then increasing it. So when you see a number out here that is a whole number, or a number greater than 1, let me note that down. This is your a value, right? The a value out there in front is what determines the vertical stretch or compression. This particular one has an a value that is greater than 1. So if you see a number out here like 2 or 5 or 7/3, anything that is bigger than 1, you end up with a vertical stretch. Which means it's going to get taller than it normally would be if it's above the axis. The thing you also have to remember, though, is that anything below the axis goes deeper. So it's taller / deeper. All right. So if I were to fetch myself a grid and get my axis on there, the basic log function, which I have over here, has a vertical asymptote at 0. When x is 0.1, log is at -1. When x is 1, log is 0. And when x is 10, log of 10 is 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 1. Now, I could sketch that in. I'm going to do the transformation first so that I don't get lines all over the place on my grid. So mathematically, the way you do this these numbers are log x. What I'm trying to sketch is 3 log x. So all I have to do is take these numbers and triple them. So -1 times 3 would be -3. 0 times 3 would be 0, and 1 times 3 is 3. And a vertical asymptote which goes to -infinity will be -infinity times 3, which is just -infinity. So what I've got here then is this dot, this one right here, that used to be at 0.1 -1 will be at 0.1 -3. And you see that's this thing. This dot was under the axis, so it is forced deeper. It is forced further away from the axis than it already was. This dot was right on the axis, so it doesn't matter. You stay right there. If you're 0 away and you make that 3 times farther, you're still 0 away. This dot was up 1, so if I triple that, make it 3 times further away, then it's up here. It is 3 times taller than it used to be. So now that I've got these dots still lining up in a logarithm pattern, I just need to color them in. So if you can see the original log passing through here, maybe I'll just dot it in for you. Do you notice that on this side of the intercept, that the pink line, the transformed logarithm, is deeper than the original was? And on this side of the intercept, the transformed function is taller than the original was, as predicted up here. For the next example, I'm going to use the base function 3 to the exponent x. So I'm going to have to make my table of basic values. So for an exponential, we usually use -1. That's a 2. -2, -1, 0, 1, and 2. And I'm not going to bother with 3 because 3 cubed would be 27, which is way off my grid. Well, what the heck? Let's put it in. So 3 to the -2 would be 1 over 3 squared. That's 1/9. 3 to the -1 would be 1 over 3. 3 to the 0 is 1, because anything to the exponent 0 is 1. 3 to the power 1 is 3. 3 squared is 9, and 3 cubed, as previously advertised, is 27. So that's 3 to the exponent x. So the function I'm going to try and transform then will be g of x is 1/2 of 3 to the exponent x. So I look at this number here and I notice that it is outside of the function and it's a multiplication factor. That makes it an a value. And this number here happens to be less than 1. So I have an a that is still a positive number but is less than 1. That means that it will be a vertical compression. Which means that when I'm done sketching this thing, the function should be shorter. Anything above the axis will be closer to the axis than it used to be, or shallower. Anything that was under the axis will be drawn up closer to it. So if I were to fetch my axis, get my untranslated axis on there. At -2, I used to be at I used to be at 1/9. At -1, I used to be at 1/3. At 0, I used to be at 1. At 1, I used to be at 3, 2, and 9, 3, 4, 5, 6, 7, 8, 9, and 3 and 27, which is way off my grid. So these dots, after I apply this transformation, should be getting shorter or shallower. So I should expect this function to be squashed closer to the axis. So how much am I squashing it by? Well, these are the values of 3 to the exponent x, and I only want half that. So half of 1/9 is 1/18. Half of a third is a sixth. Half of 1 is a half. Half of 3 is 1.5. Half of 9 is 4.5. And half of 27 is 13.5. So when x is -2, instead of a 9th, I'm at an 18th. I can't really tell the difference over here. Instead of a third, I'm at a 6th. Again, it's hard to tell. Instead of 1, I'm at half. Instead of 3, I'm at 1.5. This is where I start to see the difference in the behavior. At 2, I'm at 4.5, so 1, 2, 3, 4.5, it's about there. And when x is 3, I'm at 13.5, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13.5. So if I sketch that in, I still have this horizontal asymptote here. And my exponential takes off like so. This thing used to have a horizontal asymptote and then take off like this. And then by the time I got to this grid point, I was way off. So you notice that the transformed function is shorter or closer to the axis than the untransformed version was. For the third example, I'm going to use a rational function. So I'm going to need to generate my basic pattern for this one. With the rational, we were using -2, -1, 0, 1, and 2. Because all of these numbers end up as fractions anyway, so it doesn't matter which ones you pick. We're going to remember that 1 divided by 0 is infinite or undefined, so there's a vertical asymptote here. And so the function I'm going to sketch then with my transformation is g of x equals -5 over x. Now that doesn't look like a normal a value, so I'm going to factor it out in front. So it would look like this. So if I do that, because -5 times 1 over x would be -5 over x. If I write it this way, I can see that it's a number in front multiplying. It is not inside the function. That makes it an a value. And it is an a value that is less than 0. Now when you have an a value less than 0, I'm getting a reflection. And since it's an a value, it's a reflection this way, right? It affects the vertical direction. So what used to be up is now down, and what used to be down is now up. So I'm going to write the reflection. So vertical reflection. And since this number is greater than 1, just like the positive a values, if it's greater than 1, it's a magnification. So not only will this thing be flipped, but it will be flipped and then all of the dots will be pushed further away from the axis than they normally would be. So I'm going to need a graph here. And plot on my axis. So this one used to be at -1/2. this used to be at -1, this used to be at 1, and this used to be at 1/2. That's 1 over the x value. What I'm trying to sketch is these numbers, 1 over x, but multiplied by -5. So if I do that, -5 times that thing, -5 times -1/2, well, negative times a negative is positive, and half of 5 is 2.5. 5 times 1 would be 5. This remains an asymptote. 1 times -5 is -5. And -5 times 1/2 would be -2.5. So my dots used to be at -1/2, -1, and then a vertical asymptote this way. And it used to be 1/2 on this side, 1 on this side, and a vertical asymptote on that side. That was the basic pattern, and then you would do this. Now that I've applied this transformation with the vertical reflection, at -2, I should be at 2.5. So this dot got reflected, so it would be up here, and then it was made 5 times further away, landing at 1, 2.5 squares above the axis. This dot, 1 below, was reflected to 1 above, and then made 5 times further away from the axis. So instead of 1, it's 1, 2, 3, 4, 5. This asymptote down here used to head downwards, but then is reflected. So it is heading upwards. This dot used to be 1 above, reflect it, it's 1 below, and then quintuple its distance. Instead of 1, we're 5. 1, 2, 4, 5. This one, reflected, and then quintupled, ends at 2.5. And this vertical asymptote ends up down here instead, giving us a function that looks like this. So just penciling in the original. Notice that the entire thing has been flipped this way. So there's a reflection. What was up is now down, what was down is now up. And these distances have been made taller because of that factor of 5.
To sketch a transformed sine function, we're going to have to work with the sine pattern a little bit. So a sine pattern fits inside of a box that is 360 degrees long. It's a full cycle. It's like a trip all the way around a circle. That box has a midline. And your sine function fits in it like this. It zeroes out on both ends and zeroes out dead center. It has a peak halfway between those and a trough halfway between those. So you end up with 1, 2, 3, 4, 4 equally sized sections. So once you draw this box, you just have to cut it up into 4 bits. So I need to get that box onto this grid here first. So I'm going to draw myself an axis, like so. Y-axis. Now this shape is 360 units long. If I use a scale that goes 1, 2, 3, 4, 5, I'm never going to get there. So I have to jump by a sizable chunk on each one of these grid lines in order to actually fit 360 on there. So generally, the one I found that works best is if every step that way, you call it 30 degrees. So this isn't 1, it's 30. 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330, 360. And going the other way, 30, 60, 90, 120, 150, 180, 210, 240, 270, etc. Now, if I've already changed the X scale, I'm going to change the Y scale as well, just so I can get a curve that's tall enough that I can really see what's going on. I'm going to use 0.5 as each step on my Y-axis. So 1.5, 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5, negative 1, negative 2, 3, 4, 5. Okay. So the first thing I'm going to think about drawing is sine of x, not sine of 2x. So to do that, I need to get this rectangle on here. But there's been no translation, so I'm counting from the basic axis. I need to draw a rectangle that's 360 degrees long. So I go out to 360 degrees here. And I'm going to draw myself the back end of this rectangle. And you can see that the curve is going to have a line where the peaks land, and it is up 1 from the midline, and the troughs land down 1 from the midline. So I'm going to draw that in. So I know that all my peaks will land on this line. All of my troughs will land on that line. Now, if we were just sketching sine x, I would just have to map this pattern into this rectangle. 0 out at the beginning, 0 out at the end, 0 dead center, peak halfway, trough halfway, and then I would have my curve. But sine 2x means that there are 2 full cycles in 360 degrees. This number here, the k value, that makes the function faster. Right? The x's are happening twice as quickly as they normally would. So you get twice as much function in the same amount of space. So to handle that, I'm just going to take this rectangle here, and I'm going to allow for there to be 2 full cycles. I'm going to split it into 2 even pieces. So 1, 2, 3, 4, 5, 6 squares each. So if I go this way, 1, 2, 3, 4, 5, 6 here. 1, 2, 3, 4, 5, 6 here. Right at the edge. And now that I've established this little rectangle here, I have to fit this pattern into this shortened box. So the pattern was 0 out at the beginning, 0 out at the end, be it 0 exactly halfway. Your first peak happens dead center between these 2 dots, and your trough ends up exactly halfway between these. So you've got enough there that you can draw in your sine curve. And you can see my choice of using half a unit per notch on here has made it tall enough that I can actually see that it curves. Once you have it in one box, you have to put it in all the rest of them. So 0 at the beginning, 0 at the end, 0 in the middle, 2, 3, 4, 2, 3. Peak halfway, trough halfway. Next box, start 0, end 0, 0 halfway, peak in the middle, drop in the middle, connect the dots, and start at 0, end at 0, halfway, 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 and you get a beautiful picture of a sine curve. And most of that work was setting up the grid, trying to figure out that you should step by 30s and go up by halves. Counting out a rectangle. And once you get the rectangle counted out, you just have to plot those 5 dots in there and then make your way through.